Hydrolysis is the reaction of an ion with water to produce either the conjugate base of the ion and a hydronium ion, or the conjugate acid of the ion and a hydroxide ion. In this reaction, we can see how acetate is reacting with water to produce its conjugate acid and hydroxide. Since a neutral salt contains both a spectator cation and a spectator anion, no reaction occurs, producing a neutral solution. A neutral salt contains the cation of a strong base, which are group 1 ions and group 2 ions, except beryllium. A neutral salt also contains the anion of a strong monoprotic acid, which also acts like a spectator in water. A salt containing the anion of a strong monoprotic acid and the cation of a strong base will produce a neutral solution in water because neither of the ions undergoes hydrolysis. For example, we can look at sodium chloride, which is neutral in water. Sodium is a group 1 ion and chloride is the anion of a strong monoprotic acid. Basic salts contain the anion of a weak monoprotic acid and the cation of a strong base. They produce a basic solution in water because the anion acts as a weak base producing hydroxide ions and the cation does not react. We can look at a solution of magnesium cyanide as an example. Magnesium is a spectator ion, and cyanide reacts with water to form hydrocyanic acid and hydroxide. This produces a basic solution. Acidic salts occur when a salt is produced from a cation that is the conjugate acid of a weak base and an anion that is the conjugate base of a strong monoprotic acid. They produce an acidic solution in water because the cation acts as a weak acid, producing hydronium ions, and the anion does not react. In our example, we can see how the cation acts as a weak acid. The anion will not react. Some metal cations can act as weak acids when they are surrounded by water in their hydrated form. The ions must have a small size and relatively large charge, leading to a high charge density. This causes the oxygens of the attached water molecules to be drawn very close to the cation, which polarizes an OH bond. This increases the tendency of the molecules to donate protons. In our example, we can see how the chloride ion will not react, while the chromium-3 ion will create a hydration shell. This allows it to act as a weak acid. Let's take a closer look at one of these problems. Here it is a 6 molar iron 3 nitrate solution. We start off by writing the dissociation equation, which allows us to see the ions formed when the salt is in solution. Nitrate is the anion of a strong monoprotic acid, so it will be a spectator. Iron 3, on the other hand, will form a hydrated ion. We then create an ice table where the hydrated ion is acting as a weak acid. We fill in the initial concentrations, and the changes to those will be X. When we put the equilibrium concentrations into the Ka expression, the change to the initial hydrated iron ion concentration is negligible because the percent ionization comes out to be less than 5%. Once we have the concentration of hydronium, we can then find the pH. When a salt has a cation that is a weak acid and the anion that is a weak base, we must look at the Ka value for the cation and the Kb value of the anion. The solution is acidic if the Ka of the cation is greater than the Kb of the anion. If the Ka of the cation is less than the Kb of the anion, the solution is basic. If both values are the same, it is neutral. In these problems, we need to create two hydrolysis equations and compare the Ka and Kb values to determine the condition of the solution. Determine if an aqueous solution of chromium-3 acetate will be acidic, basic, or neutral. Well, both the cation and the anion will react with water, so we need to make two hydrolysis reactions. Once we have our Ka and Kb values, which we would get from the acid-base table, we can compare them. Since the Ka of the cation is greater than the Kb of the anion, the solution will be acidic. A salt containing a cation of a strong base and an amphiprotic anion will produce a solution that is acidic when the Ka for the anion is greater than the Kb for the anion, or basic when the Ka for the anion is less than the Kb for the anion. Since the cation is from a strong base, it will play no role in determining the condition of the solution. It is simply a spectator. We will need to create two equations because the anion is amphiprotic. In one equation, hydronium will be formed, and in the other, hydroxide will be formed. We can then compare the Ka and Kb values. Determine if a 0.10 molar solution of sodium dihydrogen phosphate will be acidic or basic. We first write our two hydrolysis equations. In one of them, dihydrogen phosphate will be acting as a weak acid and donate a proton to water. In the other, it will be accepting a proton from water. When we have our Ka and Kb values, we can simply compare them to each other. Since the Ka is greater than the Kb, the solution will be acidic. Most biological solutions, such as your blood, require their pH to be maintained within a narrow range. They're able to do this using buffers. An acid-base buffer is a solution that resists changes in pH following the addition of relatively small amounts of a strong acid or base. A buffer contains a weak acid-base conjugate pair. For instance, let's look at a 1 liter solution of 0.10 molar hydrofluoric acid. Only a small percentage is ionized due to it being a weak acid. What would happen is a solution could neutralize the addition of a base but not an acid, because the concentration of the conjugate base is so low. The issue can be fixed by adding a soluble salt of the fluoride anion so that we have more of the conjugate base. Le Chatelier's principle states that the equilibrium will now shift left and further suppress the minimal ionization of the weak acid. This is an example of the common ion effect. Since the percentage ionization of the acid and the hydrolysis of the base are so low, we can assume the equilibrium concentrations of the acid and base are equal to the initial concentrations. Therefore, our solution contains both hydrofluoric acid and fluoride with a concentration of 0.10 molar. Let's calculate the pH of the solution.
We always start by writing the chemical equation, and it is easiest if we start with the acid every time.
Then we create an icebox and plug our values into the Ka expression. We find the concentration of hydronium, which we use to get our pH. A buffer solution normally consists of a weak acid and its conjugate weak base in appreciable and approximately equal concentrations. We assume the equilibrium acid and base concentrations are equal to the initial concentrations due to the common ion effect. Appreciable quantities of each component allow the solution to resist large pH changes equally well when small amounts of either a strong acid or base are added. Buffers can be referred to as being either acidic or basic, based on which region of the pH scale they buffer a solution in.
To determine whether a buffer will be effective over an acidic or basic range, we can look at the pKa of the weak acid component. If the ratio is close to 1, the pH equals the pKa.
To come up with an equation to tell us the hydronium concentration of the buffer, we can simply rearrange the Ka expression. From this we can tell that the hydronium concentration only varies depending on the Ka value of the weak acid and the ratio of the weak acid to its conjugate base. If this ratio is 1, then the hydronium concentration equals a Ka value. In other words, the pH equals the pKa. At a constant temperature, Ka won't change, and the only thing that can affect the hydronium concentration is the acid-base ratio. Diluting will not affect the ratio because it reduces the acid and base concentrations equally. We can do the same thing for a basic buffer by rearranging the Kb expression. Similar to the hydronium concentration of the acidic buffer, the hydroxide concentration only depends on the Kb value and the ratio of the weak base to its conjugate acid.
However, rather than using those equations, we can instead refer to the Henderson-Hasselbalch equation. The derivation begins with our rearranged Ka expression, and we take the negative log of both sides. This puts the hydronium concentration and Ka value in terms of pH and pKa. It is important to recognize that we invert the ratio when the sign of the log is changed. It is now base to acid. We can use this equation for any conjugate acid-base pair, but note that this equation is for buffers only.
Let's use our hydrofluoric example from earlier to see what happens when we add an acid to a buffer. If we add 0.010 mol of hydrochloric acid, we can create an ICF table or Newt box to get the final concentrations. This is a neutralization reaction because the fluoride ion will neutralize the added acid. The reaction goes to completion and we use a single arrow instead of the double one we used for the icebox. After filling in the initial row, we can see that the hydronium will be the limiting reactant. We then fill in the values in the change and final row, taking care to remember proper sig-fig rules. Now we can use the Henderson-Hasselbalch equation to get the pH. The pH has decreased, which makes sense since we added an acid.
Although the pH has gone down, the decrease is very small.
In fact, the hydronium concentration here has only gone up by a factor of about 1.2 times. If we were to add the same amount of hydrochloric acid to pure water, the pH would decrease from 7 to 2. To appreciate how effective this buffer is, that represents an increase in the hydronium concentration of 100,000 times. Adding a strong base essentially works the same way as adding the strong acid. This time, the hydrofluoric acid neutralizes the added hydroxide. We still use an ICF table and the Henderson-Hasselbalch equation. Since it is base being added, we would expect the pH to increase slightly, and this is indeed the case. This diagram is a good summary and visual representation for our examples above, although in this case the weak acid is ammonium and the weak base is ammonia. On the left, adding hydroxide raises the pH slightly. On the right, adding hydronium lowers the pH slightly. A buffer's resistance to change in pH depends solely on the absolute concentrations of its components. A higher concentration of a weak acid and its conjugate base means a buffer can neutralize a more strong acid or base before its pH changes significantly. A low-capacity buffer with the same ratio as a high-capacity buffer would experience a greater change in pH following the addition of equal amounts of hydronium or hydroxide. To prepare a buffer, we choose a weak acid-base conjugate pair with a pKa within 1 unit of the desired pH. The pKa should be the closest one to the target pH. The more the component ratio changes, the more the solution pH changes upon addition of an acid or base. This ratio should be no larger than 10 but no smaller than 0.1. Buffers are most effective when the ratio is near 1. This is an example of a buffer calculation where we want to calculate the pH of the buffer. We are adding 150 milliliters of 0.1 molar acetic acid to 100 milliliters of 0.2 molar sodium acetate. We get the initial concentrations by using the dilution factor, and then we create an icebox to get the equilibrium concentrations. X is so small that it won't affect the acid and base concentration significantly. Now we can plug the equilibrium concentrations and Ka value of the acetic acid into the Henderson-Hasselbalch equation to give us the pH of the buffer.
Note that the same answer results from just plugging our values into the Ka expression.
Let's do another example where we need to find how many grams of ammonium bromide we need to add to 0.25 moles of ammonia to get a buffer with a pH of 8.95. This time we can begin with the Henderson-Hasselbalch equation. We already have the values for the pH, Ka, and ammonia concentration, so we just need to find the concentration of ammonium. We isolate it and get a concentration of 0.50 molar. Now we just need to turn it into grams. Since we want to end up with 1 unit, we start with 1 unit. In this case, it is liters, and we use the concentration, mole ratio, and molar mass to get to grams. It's very important that your blood is able to transport nutrients and oxygen to all the cells of your body, and also that it can remove carbon dioxide and other waste materials from them. Your blood must be at a pH of 7.35 for all these processes to occur correctly. Blood is made up of blood plasma and red blood cells. A protein found in red blood cells, hemoglobin, acts as a weak monoprotic acid and transports oxygen. This is how hemoglobin transports oxygen. Oxygen binds to hemoglobin, producing oxyhemoglobin. Alkalosis is when the hydronium concentration is too low. The equilibrium must shift so far to the right it causes the oxyhemoglobin concentration to be too high to allow the adequate release of oxygen. Acidosis is when the hydronium concentration is too high. The equilibrium must shift so far to the left it causes the oxyhemoglobin concentration to be too low, greatly reducing hemoglobin's ability to bind to oxygen. Here is the buffer system involving carbonic acid and bicarbonate. The body can alter its breathing to modify the concentration of dissolved carbon dioxide if the blood's pH is too low or too high. Another buffer system present in our blood includes dihydrogen phosphate and biphosphate.